Hello everybody. In this video we're going to discuss the second method, which is for evaluating the mass transfer coefficient, which is the exact laminar boundary layer analysis. And as the name implies, it is an exact solution, which means that it's not an approximate solution, and it means that it gives the actual equation. This is the main output of this method, is to get the actual equation of mass transfer coefficient in case of laminar flow for flat plate. This is one other detail that's not here, and this is for the analysis based on the boundary layer assumption, or the boundary layer theory. And to understand this, we need to understand first what we mean by the boundary layer. Boundary layer is a fluid mechanics term. And this is because fluid mechanics affects, or the degree of turbulence affects the convection in heat transfer and mass transfer. It's kind of used in both fields as well, in heat transfer and mass transfer. And this is something that I want to do a quick revision about before I start the analysis, just to make sure that everybody understands what we mean by the boundary layer. So the boundary layer, I will consider three cases, one in case of momentum transfer, one in case of heat transfer, one in case of mass transfer. And in these three cases, I have solid surface at the bottom, and there is a fluid flow in the top. In these three big areas here, there is a fluid flow in this x direction. And here I have the velocity of the fluid at the surface is 0, and this is expected because of the no slip boundary condition, which is a very famous boundary condition in fluid mechanics, that the layer of the fluid that is touching the solid surface is stagnant, or it has the same velocity as the surface, and this is what we call the no slip boundary condition. So the velocity here is 0, assuming that the surface is stagnant or stationary. And here at the bulk of the liquid, the fluid, the velocity is the maximum velocity, which I call it V infinity. The same here in heat transfer. If I have a cold surface and a hot fluid, then I will have here at the bulk of the liquid, the temperature is the maximum temperature, and the heat is transferring from the bulk of the liquid to the surface. So we have here the minimum temperature, we have here the maximum temperature, and that's why this is similar to this. I have here maximum velocity, maximum temperature, minimum temperature. The same is applicable for the case of mass transfer. If I have a fluid flowing over a surface, and this solid and this species is diffusing or transferring from the bulk of the liquid, which has a concentration of C infinity, and this is diffusing in this direction until it reaches the surface, which has the minimum concentration. So in these three cases, if you think about the difference in concentration, difference in temperature, difference in velocity, you would think that there is some sort of transition from this minimum or 0 velocity in this case to the maximum. It's not like a step increase in the concentration. So it's not 0 velocity and then the next layer is maximum. So it has some gradual change. Same here, there is some transition. And what we will see, and what we know and what we expect, is that we will have this profile of the velocity, the temperature, of the concentration, and this shows us how the velocity increases in the y direction from 0 to V maximum, how the temperature increases in y direction from 0 to, or Ts to T maximum, and the same for concentration from C minimum or Cs to C maximum. So this is a very logical, very expected thing to have. That this gradual change in the parameters from minimum to maximum. If we want to study this gradual increase in more details, we will find that this leads us to what we call the boundary layer. And we will talk about the fluid mechanics and the boundary layer. In this case, it's called hydrodynamic boundary layer. Hydrodynamic because it has something to do with the hydrodynamics of the flow. And for the hydrodynamic boundary layer, we we say that in case of fluid mechanics, we agree that the velocity here is zero and the velocity in the center is the maximum if the flow is inside a pipe like this. So the maximum velocity is in the center, the minimum is zero on the sides of the tube. And then we are very familiar with this velocity profile. This is a very famous velocity profile that we know from fluid mechanics. And we know that the velocity takes this parabolic shape. And if we take a closer look at this layer which is adjacent to the inner walls of the tube, where the velocity is changing quickly. Of course, the change in velocity is gonna be in a higher rate than it is in the bulk. So this is where the majority of the velocity change takes place. Especially if I'm discussing the turbulent flow. In case of laminar flow, this might be like a continuous change in velocity, but in case of turbulent flow, it has this quick change in the velocity from the surface to the bulk. So here you'd see that this is the minimum velocity, this is the velocity until it reaches almost the maximum value. And in this case, we can define what's called the hydrodynamic boundary layer is the thickness of the fluid adjacent to the surface of the solid, where the solid surface where the velocity is zero. And this thickness is defined so that the velocity at the end of the boundary layer equals 99% of the maximum velocity. So if the maximum velocity is 1 meter per second, so the thickness of the boundary layer is the thickness where the velocity is 0.99 meter per second, which is almost 100%, but it's very close, because it might take longer distance until it reaches the 100%. So we can define it as 99% of the maximum velocity. So this is the definition, that V equals 99% of V infinity. So this is what we mean by the hydrodynamic boundary layer, and there is some significance behind this definition actually. Sometimes we need to, or it's not sometimes, always we need to put equations to describe what's taking place in the system, either the change in velocity, either change in temperature, in pressure, whatever the parameter that you are interested in. And in this case, you want to describe the change in this parameter in like an accurate way or in a precise way. And in this case, you have to define exactly where the change is taking place. You can, of course, include the whole diameter, but what you have is taking place in a very thin layer adjacent to the surface. So if you can describe what's going on here, it's gonna describe what's going on in the whole system. If you have a change in concentration that takes place from here to here, but the majority of the change happens in here. So if you can describe this mathematically, so you are describing what's taking place in the whole system. So this is the main idea, and that's why we are really interested in this boundary layer, because it describes what is actually taking place in the system, or describes what or the area where the majority of the change is taking place, either in fluid mechanics, either in heat transfer, or in mass transfer. So this is the main merit behind the discussion of the boundary layer. So the boundary layer analysis, to understand the boundary layer, we started with what we call the leading edge. So we assume that there is a flow that's going, and it starts to touch this solid surface at the point of x equals 0. So this is what we call the leading edge. And at this leading edge, the surface has not contributed to the change in the velocity of the system, because the flow has been going before reaching this point. So at this leading edge, the velocity is the maximum velocity, and or everywhere, except for this point at this surface of the leading edge at x equals 0 and y equals 0. And at this point, the boundary layer starts to form. Whatever is beyond this boundary layer has the V infinity, but as you see, the thickness of the boundary layer starts to grow. It develops into thicker and thicker thicknesses, as we go further from the leading edge. And you see here, this is the velocity profile. The velocity is changing from 0 to maximum in this thickness here. As you proceed further towards more x or higher values of x, the thickness where the velocity is developing gets thicker, and that's why the thickness of the boundary layer increases. And this is what we mean by the boundary layer, the hydrodynamic boundary layer. So this is the developing boundary layer. It starts to develop from here, from the leading edge, and until it reaches the maximum value later. So for the boundary layer, we know that at x equals 0, which is this point, Vx and Vy equals 0. This is the no-slip boundary condition applies here for both directions, so the velocity in x and y direction is 0. And at x equals infinity, at very far distance from the leading edge, the velocity is going to be v infinity. So this is these are like fluid mechanics things that we know from the analysis of boundary layer. Now let's see how this can relate to what we are discussing regarding the mass transfer. And this is very relevant because as we said, we will have the three systems have three transitions from 0 to maximum or from minimum to maximum. In this case, we will have boundary layer for temperature and boundary layer for concentration. This is what we call the concentration boundary layer. This is what we call the thermal boundary layer. So in this case, this is the thickness where the change in concentration equals 99% of the maximum change in concentration. The same for thermal boundary layer. It's the thickness where the change in temperature is 99% of the maximum temperature change, or Ts, T infinity minus Ts. And this is kind of logical because it makes sense, or it's very similar to fluid mechanics. But there is a very important point here, is that you might have a system where you have simultaneous fluid flow with mass transfer and heat transfer. You have the three going on simultaneously, and in this case you can predict that you will have boundary layer for each one of the transfer phenomena that are going. But in this case, you have to keep in mind that there is nothing that dictates that the three boundary layers are equal. You might have different boundary layer thicknesses for the three transport phenomena for the same system. You might have for the same system thicker hydrodynamic boundary layer than the concentration boundary layer. It's totally possible to have these kind of things, because you have different parameters, you have different transfer or diffusivities for each one of them. So there is nothing that will force them to be the same. Now, if we go to the fluid mechanics regarding the flow of fluid over flat plate, we will consider the case of a steady state. These are the conditions of this analysis that we will go through. So we are now done with the understanding of what we call the boundary layer, and now we will go through the mathematical representation. So I'm gonna go for this for steady state momentum transfer. This is for momentum transfer, just to revise these equations: for incompressible flow, for continuity equation, for flow over flat plate. This is the continuity equation, and this is the equation of motion, which is the mass balance and energy balance. And this equation of motion is the general form of the equation. This is simplified, of course, but the general form of the equation of motion is the energy conservation equation. So this is mass balance and energy balance for fluid flow. And by the way, this equation of motion is the general form from which Bernoulli equation was like produced as a special case. So these are the two equations that describe the fluid flow over a flat plate. And in heat transfer, if you do the same analysis for thermal conductivity, for thermal boundary layer, for the energy transfer, for steady and compressible two-dimensional, the same conditions, you will have this equation, which is very, very similar. You'd see here, if you replace any velocity with t, and you replace the thermal diffusivity or momentum diffusivity with thermal diffusivity, it's going to be the exact same equation. In case of mass transfer, we can do the same for the same conditions, with the difference that we have constant mass diffusivity. This is the equation, and we know that NA equals negative D multiplied by dCA by dx plus CA multiplied by Vx, and this is the derivative. It's going to be the derivative of this plus the derivative of first multiplied by second, the derivative of second multiplied by first. So this is the shape of dNA by dx and dNAy by dy. These are the two terms, and we know that this is steady state equation, and we know that under the steady state equations from fluid mechanics, Vx is function of y and Vy is function of x, and that's why we will cancel these two terms. I know there are many mathematical concepts here and fluid mechanics concepts here that I didn't go through, but this is pure fluid mechanics, and this will require like single separate video to discuss, and we will not have time to go through all of these details. So if you want to know more about these, please go to any fluid mechanics textbook, and you will find all these details in like deep details how we reach these equations. But I hope you believe me that this is true, and this is the equation. And again, from fluid mechanics or from the mass transfer, we know that the concentration is changing in the in the y direction. So the change of concentration in x, or the second derivative of concentration in x direction, is much smaller than the change of concentration in y direction, or the second derivative of it. So we can ignore this term, and this is the form of the equation that we want. So just to make the long story short, this is the form of the equation that describes the concentration boundary layer. And if we put the three systems together, we'll find that they are identical with just the replacement of the parameters that we have: the temperature, concentration, velocity, and diffusivities. Put the diffusivity of the system that is suitable, and you'll find that these three equations are exactly the same, with the same boundary conditions, or very similar. You can just put do some modifications to the boundary conditions, and they're gonna be exactly the same. So in fluid mechanics, we know from fluid mechanics that there is a solution to this equation that's called the Blasius solution, and sometimes this equation is called Blasius equation because it was solved by Blasius. So Blasius did the solution to this equation, and that's why it's called Blasius solution to Blasius equation, which is a very famous solution. There are a lot of mathematical steps included, so again, I'm not gonna go through all these details, but just to make this simple and to get what we need from this, the equation that we will get is this. This is the product of the Blasius solution, and this you will find that the n, which is the flux, equals d multiplied by this bracket, which is function of Reynolds number, and x, and this multiplied by the total drive, or the overall driving force, or the driving force, which is Cs minus C infinity. And we know that in case of convection mass transfer, we have the equation is the mass transfer coefficient multiplied by the concentration difference. So this is the mass transfer coefficient, this is the concentration difference, so whatever is multiplied by it is going to be the mass transfer coefficient. So this is Kc x equals dAbx multiplied by all these parameters. We can rearrange the equation to have it k multiplied by x divided by dAb, and this is the shape of the equation. So this is the output that we want. So by looking at this solution, we will notice two main observations here. The first is that we have here Kcx, and this is Sherwood x, and this is Reynolds x, and this x means that, and this characteristic length is x. So x is the distance, and this means that I have or I use this equation to calculate the mass transfer coefficient at specific point on the surface of the flat surface. This is what we call the local mass transfer coefficient. It is dependent on the location. If I calculate it after short distance from the leading edge, it's gonna be much different from after long distance from the leading edge. So it changes with the position of the point where I am doing the calculations. So this is the first thing. The second thing is that we knew from the dimensional analysis that the general form of the equation is that Sherwood number is constant multiplied by Reynolds power constant multiplied by Schmidt number power constant. But I don't have any Schmidt number here. This is just Reynolds number. And this is true because the Blasius solution is based on the assumption that for heat transfer, it's based on the assumption that Prandtl number equals 1, and it's based on mass transfer, in case of mass transfer, on the assumption that Schmidt number equals 1. So for both cases, we assume that Prandtl and Schmidt number equals 1, and that's why it should be here, but it's equal to 1, so we don't put it because it's already equal to 1. And there is another relation that we know from from some derivation here that we will not go through as well. The Schmidt number, or we have already mentioned that Schmidt number is nu divided by dAB, which is momentum diffusivity divided by the mass diffusivity. And in this case, this is what I was mentioning, that we will not go through the details of this, that if I have the two diffusivities are equal, then the thicknesses of the two boundary layers are going to be equal. So the hydrodynamic boundary layer equals the concentration boundary layer. So in this case, we have Schmidt number equals 1, so delta equals delta C. But in general, if I have a case where Prandtl number is not equal to 1, so we have to do something else. So this is what we, or some demonstration of the boundary layers. This is the dotted line is the is the hydrodynamic boundary layer. The solid line is the concentration boundary layer. We have two cases. Schmidt number is larger than 1. In this case, we will have the hydrodynamic boundary layer thicker than the concentration boundary layer. If Schmidt number is less than 1, then we will have the opposite case, where the hydrodynamic boundary layer is thinner than the concentration boundary layer. This can be represented mathematically using this relation, which is the relation between delta and delta C is Schmidt power 1 over 3. So if I have larger value of Schmidt number, then delta is larger, which is the hydrodynamic boundary layer, and vice versa. And if this is considered during the analysis of Blasius solution, then from fluid mechanics, we know that delta equals 5x over Reynolds square root of Reynolds x. So this can give us a relation between delta C and the rest of the parameters. So I have delta C as a function of Schmidt number and Reynolds number, and from this we can find the Blasius solution, and we will find that the Schmidt number is equal to Kc multiplied by x divided by dAB equals constant multiplied by Reynolds power constant multiplied by Schmidt power constant. So this is putting everything together now. We have the equation in terms of, or in the shape that we are familiar with, and we know that this is the shape that we or the general form of the equation that we are used to. This is totally fine, but there is just one issue here when we deal with this equation, is that it's all local. So I never use this local mass transfer coefficient, or what I usually use is the overall mass transfer coefficient, or the general mass transfer coefficient for the whole surface. So to get the average mass transfer coefficient of a flat surface, we get the average by integrating the k dx divided by the integration of dx, and this is just some mathematics. And if we do the math, which is just getting the parameters together and doing the integration and simplifying the equation, we will reach this form, which is Sherwood number equals Kc multiplied by L divided by dAB, which equals 0.664 Reynolds power half Schmidt power 1 over 3. And this is the general solution for, or the exact solution based on the boundary layer analysis for the mass transfer coefficient in case of flat plate under laminar flow. So this is valid for Reynolds number less than 2 multiplied by 10 power 5. So this is almost all what we need to mention here. In the next video, we will solve an example to demonstrate more how we can use these equations. So I'll see you then, inshallah. Goodbye.